The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, and thank you for joining us on our call today. My name is Christina Spearman from Transcat, and I'll be your moderator this afternoon. Our webinar topic is Elevated Skin Temperature Screening, How to Get Back to Work Safely. This topic is being presented by Russell Hall from FLIR. Russell Hall is a channel partner manager for FLIR. He has been with FLIR almost 2 years and is a level 1 certified thermographer. Russell is based out of Wisconsin, but supports Transcat nationally. We expect today's presentation to last roughly 40 minutes, and then we'll answer any questions that have been submitted. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Russell.
Great, thanks, Christina. Appreciate that intro and having me on today to talk about elevated skin temperature. Obviously, this year with COVID-19, tracking people's temperatures and making sure that people are in facilities and safe and social distancing has been a very big topic. And at FLIR, we have these solutions available to you, so very humble to be talking about our different solutions to keep you, your families, your colleagues, everybody safe as we try to incorporate and get back to normal activities in our day-to-day lives. So with that, get rolling here. So a little of the agenda. One, FLIR, just the overview and history of our EST solutions, a little bit about FLIR and our history. The correlation between skin temperature and core body temperature. So we call it elevated skin temperature because cameras are actually seeing and detecting your skin temperature, not your core body temperature. There is a correlation to them, and we'll talk about that and some of the nuances. Also, effective EST screening system setup. So there's definitely some different steps and processes that you want to follow, some guidelines. A lot of these are set out by the FDA as well. So it's one thing to have a camera, it's another thing to use it properly. And then our FLIR EST screening technology, how we go to bat, and our different solutions. So first, a little bit of the overview of who FLIR is. So FLIR, we're about a $2 billion organization. We're a global organization, and we have products in all sorts of different sectors and industries and divisions. So we have industrial MRO, electrical, we have security solutions, and the solutions for the government and defense. So we make a lot of product for them as they go to keep us safe on a global level. A lot of our products can be broken into two different kind of categories, whether they have a thermal component or not. So about 60% of our products that we sell do have a thermal imaging camera inside of them. So at the base of it, we're a technology company, and our technology, which is generally around thermal imaging, is displayed in a bunch of our different products. So first off, a little bit about thermal IR and how we use it, and in particular for EST. Again, like I said earlier, we're looking and providing you surface temperature. This is our camera, this is anybody else's camera on the market. No thermal imaging camera can see through somebody's body and really understand what their core body temperature is. What we're picking up is your surface temperature, or when you're looking at a human, your skin temperature. So we like to call it EST, elevated skin temperature, not necessarily elevated body temperature. When you're using thermal imaging cameras for detecting elevated skin temperature, it should be meant to be used as a first line of defense. It's not a medical device. It cannot tell you that you do or do not have coronavirus. It cannot tell you that you do or do not have the flu or strep throat. But a lot of these common, maybe not so common like COVID, but these diseases and infections are associated with having an elevated skin temperature. So these cameras are meant to screen folks to make sure that everybody, certain folks have an acceptable, appropriate skin temperature. If they do, then they can go on into work, and they can go into this movie, or they can go into this grocery store. If they're elevated, or if their skin temperature is elevated, then you might want to set them aside and give them a test with an actual medical grade thermometer. Stick something in their ear, stick something under their tongue to really understand what their body temperature is. And then from that test, you'll know if they should or should not be included or pass into that facility. So, history of FLIR EST screening. So we started as AGEMA Infrared Systems back in 1968. In 1968, we had a camera that looked like this. It was big, bulky, heavy. I imagine like the Beastie Boys when they're in music videos with a boombox. Big thing, clunky, very heavy, cost about like $100,000 in 1968. We fast forward to 1998. That's when FLIR Systems is born. In 2003, there was a SARS outbreak, and so actually at that time we developed some products to be used at a regional level across the globe to detect elevated skin temperature for SARS. So we've actually been doing this for about 17 years. In 2004, we were FDA registered. All of our products that we've come out with since are also FDA registered. In 2009, again, people turned to FLIR when there was the H1N1 outbreak or the swine flu. Again, airports, bus stations, train stations, all of those. People looked at FLIR and said, hey, we want to make sure that the people getting on these planes or traveling or coming in this building are safe and healthy. So again, FLIR was looked at to provide those solutions, and we continued to develop our solutions. In 2014, again, with the Ebola outbreak, came out with some more solutions, more precise, better accuracy. Obviously now here in 2020, in particular for the United States, this is out of the, the four outbreaks that we're talking about here on this slide. This is the one that has really impacted the United States the most, and definitely the globe the most. So again, we've been looked at as the worldwide leaders in thermal imaging technology, and we're coming out with more and more solutions to better serve people, really on this planet. So now if we just look at 2020 by itself, where we were in January. So before, COVID really started rearing its ugly head, our traditional cameras in January, and a camera that maybe you bought last year or 2 years ago, maybe you knew it, maybe you don't, but if you bought a camera in the last 5-10 years, it's a professional camera. Not all of our smaller cameras, but screening mode is on there. So screening mode is a feature on that camera that you can use to screen individuals. So if you bought something last year and you're like, oh man, I don't want to buy another camera, you probably don't have to. You already have that. It's just a setting that you can get to in your cameras. So up until January, and with the exception of some of these different outbreaks in 2004 and 2009, 2003, 99% of the cameras that we sell were for predictive, preventative maintenance. When you're looking at electrical panels, motors, housing inspections, all of that. 1% were kind of, hey, I really like the screening mode. I'm going to take people's temperatures. For us, people, assuming that everybody on the call here is in the United States, probably never really had your temperature taken before you came into a restaurant. Now that is becoming more and more common. So turn to March, we have the coronavirus outbreak. Touch ground in the United States, at least the first documented one. So quickly, what we did in May was we advanced our screening capabilities. So we came out with some new firmware updates. And then in June, we actually came out with a new software to better screen individuals, and I can do a demonstration of this here later on the call. July, again, new products, new firmware updates to make the screening faster, more efficient, and more accurate with keeping people safe. August, we just released some new products that are EST specific. So these cameras are solely meant for EST applications, what is nice about that is it kind of limits some of the confusion because we do have a lot of products and different solutions. And also we're able to drive the cost down a little bit on these products and offer it to you consumers at a lower MSRP, because we take out a lot of the features and benefits that are not needed. Our traditional cameras might go from -4 degrees Fahrenheit all the way to 2,700 degrees Fahrenheit. Well, when you're just looking at a human, and humans operate around 92 to 102 degrees, having that big temperature range is not necessary. So we stripped out some of that stuff and said, hey, we want to make a more of a streamlined solution and offer it at a better a better price. And we'll continue to develop. Yes.
We can only see the title slide. I don't know if you switched slides, but we're just seeing the title slide. We are good now. Perfect. Okay.
Okay.
You go back to it.
Okay. Did anybody chat in? If they would be
no, I haven't received anything. So
okay.
It should be good. I'm seeing now that you're advancing, so we should be all set. Apologize for that technical glitch, everyone, but back to the presentation.
Perfect. Okay. Yeah, in the interest of time, we'll just kind of keep going. So sorry if that wasn't working for you. I think I was right here. So we're actually coming out with some new products as well. So we're still investing in some of these solutions. We don't think that this is necessarily going away. And, who knows what this new normal is really going to look like. As we get back to normal travel and airports and big gatherings at baseball parks or football stadiums, all of that stuff. So we still are developing some new solutions. So the different markets and customer types, and Christina, just again real quick, you see this new slide.
Yep, we're good.
And customer types. Okay.
Perfect.
So it's really across the board, right? Like we've all learned, the last 6-7 months is, small groups, social distance. And so that goes for if you're in a manufacturing plant, if you're at a sporting event, if you're at an office building, anything like that. It's really all markets and customer types. At FLIR, and what I talked about earlier, we do industrial stuff, we do stuff for the government and defense, we do stuff for security. We like to compartmentalize into these different groups. But when it comes to EST, it really touches everybody, right? It's wherever people congregate, and there's more than 10 people in a space. So it's really applicable all over. So now the correlation between between skin and core body temperature. So this is actually an ISO standard that you're seeing here with this gentleman under this the thermal image of this gentleman. So the best correlation between core body temperature, your skin temperature and your core body temperature is actually the canthus of your eyes. So if we're out in the sun for a long time, right, our skin, our forehead tends to heat up. If it's very cold outside, our skin temperature, our nose, our ears, right, even our fingers, those are the things that get coldest first or the fastest. So when we're looking for that correlation between what my skin temperature is, i.e. what a thermal imaging camera can actually see and measure, versus what my body temperature is, we see that the canthus of the eye is actually the most stable. It's not going to heat up because of the sun, and it's not necessarily going to cool down because it's cold outside. So right in the canthus of the eye is going to be the most stable and draw the biggest correlation to your body temperature. So again, you could artificially, or because of different environmental factors, your nose could read, 80 degrees because it's very cold outside, and say, well, your nose is 80 degrees, but I don't know if that means you have a fever or not. Or you could be baking out in the sun and your nose could say 110 degrees, but your core body temperature could actually, be normal, like 98 degrees. So what we see is the most stable reading on your face, anywhere on your body, is the inner canthus of where your tear ducts are. And so again, this is an ISO standard. It's been proven out by medical professionals and researchers alike. So again, here's just another different image. You can see this gentleman where the very white and yellow around his eyes, that's going to indicate the hottest temperature. And then you have this box around here, that's going to be a lower temperature. So if you have a system that's simply scanning just forehead temperature, it's not going to be that accurate as far as what that means for your body temperature. Now, when we're all kids, right, you wake up in the morning and you're sick, and either you're really sick or you don't want to go to school, depending on what it was, your mom or your dad, they might come up to you and they put their hand against your forehead to kind of feel if you're warm, right? And so that is how we, one of the first ways that we actually think about if somebody is sick or has an elevated temperature. But just doing the forehead alone isn't going to be enough when you're using thermal imaging cameras. So you're actually going to be more accurate if your parent or guardian could actually touch and feel your eyeball or your tear duct. They would have a better indication if you really were sick or not. And some of these environmental factors that make this a challenge are, if you have a hat on for a long time, if you have hair in front of your face, if you're sweating, right? Sweating is supposed to cool us off. So if you have sweat beads running on your forehead, it's actually cooling your body off. One of the other things is that healthy skin temperature can vary. We did a couple tests and trials at FLIR. These temperatures are in Celsius, but we actually measured the temperature of about 70, 75 individuals and plotted them here. All these individuals, they're actually tested with a medical grade thermometer, and all did not have an elevated or temperature or a fever. So they're all healthy individuals. But we can see here that their skin temperature does fluctuate quite a bit, anywhere from 33.7 degrees all the way up to about 35.6 degrees. So about a 2 degrees Celsius swing, but yet all of these individuals are healthy. So what makes skin temperature vary? So it could be your gender, your ethnicity, the time of day. If you're on a normal sleep schedule where you're sleeping, maybe from 10 o'clock at night till 6 or 7 in the morning. I'm in Wisconsin. Last night it was 50 degrees outside, so I slept with the windows open, right? So as I'm sleeping, my body's at rest. I got cool air coming through my windows into my bedroom. My body's going to be very relaxed, very cool. My core body temperature is actually going to drop a little bit during the hours that I'm sleeping. Now, when I get up out of bed and I take a shower and I take the dog for a walk, drink a cup of coffee, do whatever, start stressing out about work, now your body temperature is actually going to raise a little bit. So the temperature changes throughout the day, and then it also depends person to person. Again, like I said, whether you're a man or female, if you work out a lot, if you don't work out a lot, type of foods that you eat. So there could be this range of healthy or appropriate skin temperatures. So with that said, maybe it's like, well, how do we detect anybody that is sick if everybody's different, right? And so we'll get there. But one of the other things I want to talk about is effective EST screening. So there's guidelines out from the FDA. They want to make sure that you have a camera that is accurate enough. So their threshold is plus or minus 0.9 degrees Fahrenheit. Our cameras are all plus or minus 0.5 degrees Fahrenheit, so we're well within that range. You want a stable camera. You point a camera at something that says this is 100 degrees, and then you point it back at that same thing that hasn't changed a minute later, and it still says, yes, this is 100 degrees. If it says, oh, now I'm seeing 101, right? Or, oh, now I'm seeing 99, right? That's not a very stable camera. I have a scale in my bathroom. And I don't know, maybe I'm just a little crazy or, OCD about it, but every time I check my weight, I usually jump on the scale twice. I'll check my weight. It says, X number of pounds, and then I hop off, let it reset, and then I jump back on and make sure that it's the same, right? But if you had a scale that said, you'd hop on and it says 150 pounds, and then you step off, and then you jump back on, it says, 148 pounds, you're like, oh, what's right? You hop on again, it says 152 pounds. You'll never know what's right. So just like a scale, you want to be stable and reliable, and because you haven't eaten, drinking, or, picked up a weight, every time you hop on that scale, within a few seconds, it should be the same weight. Just like our cameras, every time you point it at the same person in a, certain amount of time, or the same object that hasn't changed, you should be getting the same temperature reading. And then lastly, the big thing here that I have highlighted in red is that the technology is only meant to be used for one subject at a time. That means pointing one camera at one person and getting that person's temperature. Not using one camera and having 10 people in the field of view and trying to detect all 10 persons' temperatures. That is not going to work. It's not effective. It's not accurate. So that is a big thing. Even the FDA claims, one-to-one ratio, one camera to one person being screened at a time. So now we'll go through a couple different pictures here, different scenarios, again, as it relates to what your screening process and setup should be. So first is passive versus active screening. So there's claims out there that the subject being screened does not need to pause or look directly at the camera. So that would be an example of a passive screening. So what I have here is one of my colleagues, which is doing just that. He's not really looking at the camera. He's kind of looking off to the side. He's got a hat on. He's got glasses on, whatever. And what we can see here, if you can see this red crosshair that's right on the bridge of his nose, the temperature that is being read is this third temperature here, where it's got the silhouette of a person. It's 96.3 degrees. We'll talk about these other temperatures later. But right now, it's saying that he's 96.3 degrees. And again, we're talking skin temperature. So if it's body temperature, you say, wow, that sounds really cold. But again, we're talking skin temperature. The skin temperature is going to be a little colder than the body temperature because it's not enclosed by our skin, our outer skin, or it's not enclosed by our skin and our bones and our blood and all that. The outer skin does not have that benefit. So it is going to be a little cooler. Which is normal. Now, when Rob takes off his hat, takes off his glasses, and now he's looking directly at the camera, just like I'm looking directly at the webcam, now we see that same red crosshair. Now it's getting into the canthus of his eyes, and it's saying that he's 97.9 degrees Fahrenheit. So he went from 96.3 to 97.9 degrees Fahrenheit. He took the first picture on May 11th at 12:58. Took the second picture, May 11th at 12:59. So Rob did not go run a marathon in a minute. He didn't go do 100 push-ups and jumping jacks or anything like that. He didn't, heat up his face artificially. All he simply did was look right at the camera and take his glasses off. So his body temperature didn't, just jump 1.6 degrees. It's just the fact that in the first time he took his temperature, the camera could only pick up so much of his face that it only read what it could. But now when he presents himself to the camera in that nice one-to-one relationship, pausing, looking right at the camera, you get a better indication of what that temperature really is. Now at 97.9 degrees, that still doesn't mean that he's sick, but if we were missing people at a 1.6 degree Fahrenheit difference, that would be cause for concern. Potentially those people are coming through into your workplace with that elevated temperature and potentially carrying an infectious disease. So the result of doing a passive screen instead of an active screen is that it'll lead the camera to missing sensitive data around the inner canthus of the eye and ultimately give you poor results. So glasses on versus glasses off. There's some claims out there where you'll see some hero images or data sheets or whatever, different companies that say you don't have to remove your eyewear, our camera can still detect you, and so can the facial recognition. So yes, there's facial recognition. We all have, iPhones or smartphones, and you look at your phone now and then it unlocks your phone, right? It does facial recognition. Our software can do facial recognition, and there's other competitors out there that can do facial recognition, and that's great. But the ones that say, you don't need to take your glasses off, or you shouldn't take your glasses off, those are the ones that you want to look out for. So just like no IR camera in the market can actually take our body temperature, it can only take our skin temperature. Likewise, no thermal imaging camera on the market can see through glass. When an IR sensor hits glass, whether it's eyeglasses, a window, sunglasses, rec specs, anything, work goggles, it hits that surface and it actually ricochets off and bounces right off. So it's not taking the temperature of what's behind those glasses or behind that window. It's actually reflecting off and really kind of grabbing the temperature of something else, and or just what the surface of your glasses are. So this is a different colleague and his son. So we just took a picture of his son. We can see this white crosshair is saying that it's 75.6 degrees. And this white crosshair is right on, his glasses, right where his eyeballs would be. Now, same person, when we take those glasses off, we put the crosshair at, relatively the same spot, we see that, oh, it's 96.1 degrees. So for those videos that maybe you've seen, or those pictures that maybe you've seen when a manufacturer is claiming, we have facial recognition and we can take your temperature, and you don't have to take your eyeglasses off, you don't have to do this, you don't have to do that, we do 10 people at a time. It's not going to work. You're not going to get good results. There's a difference between checking a box and saying that you have an elevated skin temperature system and actually implementing a good sound test and actually looking for people that might be sick and carrying that infectious disease. So absolutely, you have to take your glasses off if you want a good, effective screening. So the result, thermal cameras cannot see behind glasses as the IR detectors are reflected off of that surface. So again, this child, he's not sick. I'm not saying he's sick, but I'm just saying if somebody was sick and they were hiding behind their glasses, you would never know it. That person would pass through, would get a, quote unquote, clean bill of health, and then potentially infect everybody around them as they came into that building and interacting with those people. Focused versus unfocused. Again, claim our camera can screen multiple people at various distances from the camera. So got an image of an unfocused picture here. We kind of make out the silhouette. We see the shoulders, we see the neck. Kind of looks like a head. Maybe you can see some of this hair. Okay, it's a person, right? It's not a dog and it's not an electrical panel. It looks like a person. And we're picking up or reading around their eyes, around the middle of their face, potentially their eyes, and it's saying 93.7 degrees. Now, when we do the same person, again, and all we're doing here is just focusing the camera. So same distance away from the camera, same everything, but now it's just in focus. We see that this woman is actually 95.7 degrees is that hottest temperature. So again, a jump from 93.7 to 95.7 just by having her in focus. So and a good way to kind of relate this. I got married 3 years ago, and I think a lot of people have maybe a picture, if you did pictures before, right after the wedding, where you have the bride, the most important person of the day, right? Everybody cares about the bride. And so we have this picture of the bride, my wife, standing like 5 feet away from our photographer, and then me kind of hanging out, 15 feet behind her. And it's one of those cool pictures where, she zooms in and kind of focuses on the bride, and then you see me off in the distance, and you can just kind of tell that I'm there. But you can't really make out many details. You can see my suit. You can kind of tell that it's me, but you wouldn't be able to know if I was blinking or, or smiling very big, or if I had something in my teeth, right? But it's like we're focusing on the bride, and then, oh yeah, Russell was there that day too, right? It's just my participation award. So I think there's like a lot of those kind of wedding photos. Or same thing if you're, at a scenic place. Maybe you're focusing on the person that's close to you, and then like mountains are off the distance, right? But that's not very focused because cameras, any digital camera, can only focus on one thing at a time. Same thing with our thermal imaging cameras. They can only focus on one thing at a time. Even our eyeballs, right? You could play tricks on your own eyes. You look at something close to you, everything in the back fades away. You look at something far away, everything in close to you kind of fades out. So it's important that, when we're doing these screens, that we're doing one person at a time from a fixed distance, whether it's 3 feet, 4 feet, 5 feet, and that distance is constant. When you have multiple people in a frame, they're all inherently at different distances. So you might have a camera that's at, 0.0, right? And then one person that's 5 feet away, and the second person that's 10 feet away, and a third person that's 15 feet away. And you'll see these product videos of a camera giving a temperature reading for each one of those people, even though they're at all different distances from the camera. The camera is really only getting maybe one good reading of a person at one fixed distance. Anybody else at a different distance is not going to have a good reading. So the result of doing focus versus unfocus is that a thermal imaging camera can only focus at one distance at a time, leaving other readings out of focus and or inaccurate. And again, in this case, the more inaccuracy you have, the more risk that you have that somebody with an infectious disease is coming into your place of work or wherever you're at. Distance to spot ratio. So claim, our camera can be used from greater than 6 feet away. And so a couple things with distance to spot ratio. Really what it means is our cameras, and again, any thermal imaging camera, they have a certain fixed distance to spot ratio. And it might be, 100 to 1. That means that from 100 inches away, your camera can display you an accurate temperature reading of a target that's like a 1-inch diameter. So, 100 inches to 1 inches. Or if it was 100 feet away, then you would see a temperature target of 1 foot, right? So 1 foot in diameter. So you could have something that's, as low as like 24 to 1, or 100 to 1, or 1,000 to 1. So if you have a camera that's like 1,000 to 1, that means from 1,000 inches away, which is almost 100 feet, close to 100 feet, you can see a target that is actually a 1-inch diameter size. So that would be pretty powerful, right? That's a pretty good camera. And so when we're doing these readings, when we're doing these screens, we do need a strong spot or distance to spot ratio, because the area of interest, or the thing that we're really taking a temperature of, again, that's going to be the best correlation to our body temperature, is our tear duct. And our tear duct is, it's tiny. It's like 0.005 millimeters. So it's very, very tiny. So you need a camera with a good distance to spot ratio. This one's a little harder to show you, to illustrate, but you see a picture. This is actually a picture of myself, and I have this camera on here, and it's drawing a circle around it. And I have the camera portrayed as very small, meaning like it's farther away. So the farther away that I am, the bigger sample size on a person's face that we're going to get. So you can see that the average in this circle, the average temperature in this circle is 91.3 degrees. Now, it's roughly the same picture, but now representing it with a camera that appears to be closer to you, right? A camera that appears to be closer to you, Now, we're able to get a tighter target. We're able to see, a smaller space from a greater distance. Now we can see that that spot is actually 95.3 degrees. So here it's telling us that our average, our temperature is 91.3. But when we get tighter to that target, when we get, a better reading, a better camera at a closer distance, 3 to 6 feet, 6 feet max, we're going to get more accurate readings. So 95.3 degrees, and now we can take that temperature and disseminate whether it's a good temperature or not. So result, at more than 6 feet away, our thermal imaging cameras do not have strong enough distance to spot ratio and or higher resolution to accurately measure the small region of interest, which again is the ear, the inner canthus of the eye. So lastly, on setting up a good system, right? These are some of the things that you might see out there, on the marketplace today, right? These images of, hey, here's our camera, and I'm reading temperatures of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 individuals, right? One of these gentlemen here, he's got a mask on, he's got glasses on. We just learned that if you have glasses on, you're not going to get a good temperature reading. There's people back here that, are way out of focus, like that wedding picture I was talking about. These people back here, like, we can hardly see any detail about them. The same is true with the thermal imaging detector. It's not picking up good detail of these people. You got way too many people on the screen at one time. They're at different focus lengths, too far away from the camera where the detector is not strong enough to get those readings. Same thing here, right? Glasses on, glasses on, glasses on. People way back here in the back, right? And they say, oh, 36.2 degrees, 36.3 degrees, 36.3 degrees, 36. These are not going to be accurate. At best, they're taking an average temperature of, of your face, but they're not going to find that highest temperature. And more than likely, it's just finding your face using facial recognition, which is cool. It's around these boxes. It says, hey, these are human people. It's not a dog. It's not a cat. It's a human person, which is good. Our cameras can do that too. But this is that check the box activity where you have a camera in place, but you're not doing, good system setup. You're not doing one-to-one ratios or anything like that. These people are just, being led. And then lastly, not to belabor the point, but down here, right, this camera is way up in the air. These people don't even know they're being screened. So talk about passive versus active screening. These folks aren't even looking anywhere near the camera. They don't even probably know it's there. The camera's giving you a reading of this gentleman over here, and he's not even facing you. It's the back of his head. Person with glasses on, we see the same type of thing. Again, this is a big field of view, right? Way more than 6 feet apart. Way more than, we got 10, 12 people in this screen. It's picking up their faces. It's finding out that they're humans. That's about all that it's going to be good for. And there's been some, some complaints, right? There's been some bad press about these cameras not working well. And in a lot of parts, it's a camera that's not very reliable. It's not very stable. It doesn't have very good quality. And also just the way that they're promoting to do these tests is not good. All right. So a little bit about how FLIR, how we go to business, how our technology works. So what we like to do is, just like our predictive preventative maintenance, when we're looking at motors and electrical panels or power transformers, any of this, the way that you do predictive preventative maintenance is you look for things that are out of the ordinary. You're looking for an anomaly, something that's way too hot or something that's way too cold. So if you have, your fuse panel in your house or your apartment, and you put a thermal imaging camera and you're looking at all your switches, you would expect them to all be uniform, right? All of them be like 80 degrees or 85 degrees. But if you find one that is saying, hey, this thing's 115 degrees, say, hey, something is wrong with that fuse, something is wrong with that switch. it's getting overloaded. There's too much, draw getting sent to that, or maybe it's a loose connection and it's, causing heat and turbulence. So you're looking for that anomaly. It's the same thing with screening people. We're looking for the anomaly. We're looking for somebody that is hotter than everybody else, because that might mean that they are sick. So our cameras, what they do is we actually funnel in. So there's a lot of people coming in, getting their temperature taken. So this person's 97 degrees, this person 96.3 degrees, this person 97.2 degrees, this person's, 96.8. All of these people funnel in, they get their temperature taken, and then our camera takes all of those measurements and actually averages it. So it takes all those temperature measurements and says, okay, for today, Thursday, September 24th in southern Wisconsin, a good temperature is 97.5 degrees. Then what our cameras can do, what you can set the cameras up to do, is now we want to look for somebody that's above the norm. And so you can set a threshold, or you can set a standard deviation. So what that looks like here. So this X with the line above it at 94.3 degrees. That's my average temperature. That's my 10 people come through, or my 20 people come through, and they average out to be 94.3 degrees. Then I set an alarm temperature. This is at 96.1. Now this is a fixed deviation, not a fixed temperature, not a fixed degree. So the fixed deviation that I set this at was 1.8 degrees. So 94.3 plus 1.8 gets me 96.1 degrees. So I'm saying anybody that comes through, and FLIR recommends using like 1.8 degrees Fahrenheit to 2 degrees Fahrenheit through standard deviation. What that means is anybody that comes 1.8 degrees above the norm, above the last 10 people that walk through here, hey, that's a little bit concerning. You're running hotter than everybody else. Why is that? You're the anomaly. We want to give you a further inspection and further test. And then you have the actual measured temperature. So in this case, my actual measured temperature is 95.2 degrees. So that's below the alarm, 96.1. And again, this is the first line of defense. This is the first line of screening. That person gets a green check mark. That person passes go, collects $200. They can go into work or into the ball game or wherever you're at, into the restaurant. So again, the FLIR method is we take all these temperature measurements, we average them together, and then we're looking for something outside of the norm, outside of, higher than 1.8 degrees Fahrenheit. One of the things I mentioned before was that stability is very critical, right? We talked about stepping on a scale. If I step on a scale and it says 150 pounds, if I step off and step back on, I expect it to still tell me 150 pounds. Otherwise, you have an unreliable scale. So same thing with our cameras and IR detectors. We want these IR detectors to be nice and stable. When you point it at me right now and you point it at me in a minute, I want it to read and tell me the same thing. So with our cameras, we did some tests where we pointed our cameras at a black body. A black body is a tool or mechanism that is a fixed degree. It's a known source, right? It's a known temperature. It's like a ruler. You point it at it, you set it to 100 degrees or whatever you want, and it heats up to 100 degrees and it stays constant, like turning your oven on to 325 degrees, right? It's going to hold that temperature. That is how you calibrate cameras. You use black bodies to calibrate cameras and make sure that they're stable. So we took our cameras and we just had the camera on for a period of 14 hours. These are 30 hertz cameras, so over a period of 14 hours, we're getting thousands and hundreds of thousands of data points. At 30 hertz, we're getting 30 data points each second. So what we wanted to find out was how stable were these, was our camera. What we found that was 99% of the 14 hours, and you can look at this chart, 99% of the time, our camera was within plus or minus 0.25 degrees Celsius. For 90% of those 14 hours, our camera was within plus or minus 0.15 degrees Celsius. So that is very strong, that is very accurate, that is very stable and reliable. So again, it's one of those things that speaks to the quality of the camera. You need this, because if we pointed this thing at this black body and we were getting jumps from, from 36.1 all the way to 38 and then down to 33, well, hey, that's a crapshoot, right? That's not good. You're going to let people in that are sick, or you're going to deny people that aren't sick. So you need something that is very stable. When you're assessing the accuracy of these screens, or when you're really doing the screening, you're going to have 4 different outcomes, and I have them kind of laid out here. Whether you have a hit, false alarm, miss, or a correct rejection. So what we have here is the response is related to the camera, what the camera is telling you. The camera is going to say, hey, this person has an elevated skin temperature, or this person does not have an elevated skin temperature. So yes, they have an elevated skin temperature, or no, they do not. And then the signal is, if you actually put that person up to a medical grade thermometer, what would that medical grade thermometer say? Were they over, 100.4 degrees, yes or no? So when you achieve a hit, that means that the thermal imaging camera says, hey, you have an elevated skin temperature, and then your medical grade thermometer also says, yes, you do have an elevated body temperature. That's a hit. A correct rejection is the camera says, hey, this person is, well within normal temperature range. They do not have an elevated skin temperature, and then you stick a thermometer in their mouth, and it comes out to be 98.6 degrees. And so they both agree, yes, that's a correct rejection. This person is welcome to come into work and mingle with other people. When you have a false alarm, that is, the camera says, hey, Russell walked through the camera and, he's at 99.8 degrees or whatever, and the average today was only 97. So he's well above, that average. He's at our, setting off the alarm. He's above that standard deviation. And then I go to a secondary screening and I say, I feel fine. Let me take a medical grade thermometer, stick it in my mouth. Medical grade thermometer proves me out to be healthy. So that'd be a false alarm. The camera says, hey, I think this is an issue. And then you do your secondary screening, and it turns out to not be an issue. And then lastly, you could have a miss, where the camera, says, hey, this person is healthy. They don't have an elevated skin temperature, but in reality, they do have an elevated skin temperature. They do have a fever, and they are, potentially sick or carrying that infectious disease. Again, to limit those misses, that's when you want to have a good screening process, good screening protocol in place. You want to be looking at the camera one-to-one, taking your glasses off, removing your mask, doing those things to make sure that your camera is focused, you have a reliable camera, doing all those things to make sure that you have the best test possible. Then you can avoid as many of those misses as possible. All right, really quick, we'll just look at some solutions, and then I want to show you guys a little bit of a live demo, and then we'll open it up for questions. So I'm just going to go through this really fast, I guess. So we have 3 types of cameras that can perform screening, elevated skin temperature screening. Handheld dual purpose. So this category was kind of just born this year. So these are our traditional predictive preventive maintenance that do have that functionality of EST screening. We're now calling them dual purpose. So these cameras can actually screen humans in the morning, let's say. You can get all your students into school. You can get all your employees into work. But then after everybody's in that building, everybody's been vetted. Now you can actually take this camera and go screen the boiler room, or go inspect a critical motor in your manufacturing plant. This thing is kind of the jack of all trades. They can do all of that. They're portable, you can move them around, and they have the sensitivity to do the screening for the humans. And then also that bigger temperature range, right? Now you could go down to like -4 degrees Fahrenheit all the way to like 2,700 degrees Fahrenheit. So you can do these different applications. Then we have our handheld EST specific cameras. So these are the ones that are lower priced, The body styles look the same, right? It's the same chassis, if you will. But we strip out some of those features and benefits so we can get a more cost-effective solution out to the market. But now these are going to be more limited in what they can do. The temperature range is only going to be 59 to 113 degrees. So when you want to point this at something that might be like 500 degrees, you're just not going to be able to read that. Won't give you that that resolution. And then fixed mount. So these are, you can mount them. There's no screen on board, but these can be like integrated into a network system, that type of stuff. And they'll be specific to EST. So they'll have, again, that smaller temperature range, that 59 to 113 degree temperature range, as we're only interested in looking at humans, which tend to operate around 100 degrees, give or take. All of these solutions, any of the handhelds and these fixed mount ones, can also be mounted on a tripod. So you don't, we call them handheld, but you don't have to actually be standing there holding these in your hands to perform the test. There's a universal tripod mount that comes with them, and you can mount it onto any tripod you can find. We also sell some tripods at FLIR. All right. Now I am going to pop into what screening might actually look like, and I apologize, my computer is going a little slow. So over here to my right, I actually have one of my cameras, one of these handheld cameras, actually on a tripod. So you can see me, and Christina, if you would, can you see my screen and you can see me in live?
Yep, we can see it.
Okay, perfect. So there's two images that you're seeing. One, you're seeing me in visual light, and then also this small box up here, you're seeing in thermal. So when I come in more to the field of view, you'll see me in thermal. So when I do my active screen, when I come and actually look at the camera, it's going to read my temperature. So it finds my face and boom, clear, have a nice day. So it's very fast, right? It kind of tells you where to put your face. Boom, find me, clear, have a nice day. And it's just this fast. These cameras will find you, and it's probably, maybe even comes over a little slower on the screen just because we're on this webinar. But it's very quick, basically under a second once you get into that field of view. So that is what the person being screened would see. And then here's a little bit of the back end software of it. So it's very customizable. It's pretty cool. And I'll show you a little bit about what that looks like. So this is our Screen EST software. So all of this, it was showing up, clear, have a nice day. All of this is actually customizable. So I can type in anything here, right? Thank you for attending, the webinar. Here's where I put in my allowed deviation. So I have this set at 1.8 degrees Fahrenheit. I can change this from Fahrenheit to Celsius if I wanted. There's different languages, all of that stuff. You can show these secondary images, right? So you're getting a visual image and a thermal image. You can turn that on or off. I have these checked that kind of say, take your glasses off, take your mask off, take a hat off. But if I want to just say take your glasses off, we'll kind of see that change a little bit. Back here, we'll see what our average temperature is. So right now our value is 95.46. That's our average temperature. I have my deviation set at 1.8. So if anybody came in that was 97.26 degrees or higher, they would flag this thing and it would it would give them a like a do not enter. So now when I hop back in, takes my temperature, clear, thank you for attending, right? So it's very customizable, very easy to use, very fast, very effective. Now you can see I took out a couple of those warnings. I still want it. I still want to keep these, remove the glasses. That's definitely going to be the most important thing when somebody's being screened, that their glasses are off and that they're looking one-on-one at the camera. The play on this video, so this is one of our videos, but just like we saw, saw me demonstrate, this is how it works, right? So this is at a line of people. I don't have, anybody at the house right now, but you can see this line of people walking through, getting their temperature taken. Takes it in a quick second, under a second, and then they're off to the races. This video is buffering a little bit, so it's probably come over a little bit slow. But, boom, quick, remove the glasses, find your face, green check mark, you're good to go into work. Step up to the plate, boom, find your face, you're good to go. Pause for a second, catch your temperature, you're good to go. So with it being this fast and with us, supposed to be 6 feet apart and social distancing, you can really screen a lot of people in a short amount of time. With that, Christina, I will put it back to you for any questions that we might have.
All right, thanks, Russell. That concludes our presentation portion of the webinar. We'll now move into the question and answer session. Just as a reminder, if you would like to ask a question, please send it through the question box in your webinar controls. Let's move on to the first question. Can thermal imaging be dangerous to humans?
Good question. So, it can. Our solutions are not. So a lot of thermal imaging cameras, they do have lasers on them. And so if you were pointing a laser at somebody's eye, you could cause some eye damage. Our cameras, when they're screening people, the laser is automatically turned off. So we know that we're going to be pointing at humans. So that feature is disabled. And so it's 100% safe to point these cameras at individuals.
Okay, the next camera. What's the minimum IR resolution FLIR recommends for screening?
So we recommend minimum 320 by 240. And again, at that 3 to 6 feet range, like we talked about, we're really interested in the campus of the eye. So we need a lot of resolution. We need a good distance to spot ratio. So great question. And we find that, you can definitely accomplish that with a 320 by 240 resolution camera. Anything below that, there's some trade-offs and you're sacrificing and potentially not getting as good accuracy as you should require.
Okay. How accurate are FLIR cameras?
So our cameras are plus or minus 0.5 degrees Fahrenheit. So, and then we saw the stability chart as well, pointing at the same thing. We're going to get the same reading, pretty much all of the time. FDA, they require cameras to be as accurate as plus or minus 0.9 degrees, which is a little bit big of a swing. So we're definitely inside of that, more powerful than that at plus or minus 0.5 degrees, plus or minus 0.5 degrees Fahrenheit.
All right. Do you need to be certified to use these cameras, and is there training available?
Great question. So you don't need to be certified. There is training available. So I am a level 1 certified thermographer. You can be level 1, level 2, level 3, and different, different sections. You can be in roofing or electrical. There's different types of classes. But for screening people, you don't need a certificate. Training is available. We do have some classes, and there's definitely a lot of literature out there. And definitely reach out to your Transcat rep. I'm happy to hop on a call and do like a little webinar like this. Make sure that you're comfortable. So there is some science behind it, but once you know some of the basics, they're pretty easy to use and not that complicated.
Okay. What is the calibration frequency, and what would be the turnaround time for calibrating?
So traditionally, you want to calibrate your cameras about once a year. If you're using them like a lot, like every day, you want to stick to like that every year schedule. So, and then turnaround time, you would send your FLIR camera back to us, back to our service. We have a calibration room. It's out near Boston. It's in Nashua, New Hampshire. And then turnaround time is generally, 3 to 5 days to get your camera calibrated.
Okay. All right, that concludes our time for today. If you have any further questions or would like to find out more about Transcat's product and service offerings, please contact us at 800-828-1470 or on the web at transcat.com. Thank you for joining us today. We hope you got something out of today's presentation and that you continue to join us for future Transcat e-learning webinars. Thanks a lot, Russell. Have a great day, everyone.
Thanks, Christina. Thanks, everybody.
Bye-bye.